All right. So today, guys, we are going to talk about something called conjugates of complex, or if you want to think about it as imaginary numbers. But I'm going to begin with a warm up. So I'm going to write this problem on the board, and then I want you to pause the video, and I'd like you to try this warm up. But I will continue working on the warm up here. So after you get a chance to try, you can restart the video, and you can see how you did. So in this warm up, what I want us to do is I want us to try to simplify. This is going to work on some of the stuff from yesterday, or from the last time that we had a video. Let's try 3i to the 10th times 2 plus 5i plus 2 minus I times 2 plus I. Okay, so again, I want you to try to simplify this, pause the video, see if you can try this. One thing that you might want to recall from class the other day is that the square is that I is equal to the square root of -1. Okay, all right, let's pause the video and give this a shot. Okay, so hopefully you pause the video and try this. This is actually almost like two separate problems. It's really like we need to do something with this, we need to do something with this, and then when we're done, we need to add those two answers together. So let's see what we can do with this thing on the left side first. So let's start out with I to the 10th. Let's see if we can simplify I to the 10th. Remember the other day we were saying, hey, if you're going to simplify something like this, let's always start out with I to the 4th, because I to the 4th is 1. We talked about that pattern. It goes I, -1, I, 1. So I to the 4th is 1. So if I do I to the 4th squared, that gets me to I to the 8th, and then I have an I squared left over. Okay, so I squared is -1, so this becomes 1 times -1. So I to the 10th is just -1. So really what this becomes, this whole entire part at the beginning becomes a -3. It's 3 times -1. So this is really -3 times 2 plus 5i. And then what I can do from here is I can distribute this -3. So this gives me -6. -3 times +5 is -15. And then there's an I. Okay, so we have that. That's what we get for the first part. And I'm going to bring this plus sign down. And then with the second part, these are two sets of parentheses that need to be multiplied together. So remember, we said the other day in the video, if you have two sets of parentheses that need to be multiplied together, let's FOIL. Okay, so let's try it. We can go first, 2 times 2 is 4, times the outside, 2 times +I is plus 2i. Inside, -I times 2 is -2i. And then -I times +I. Well, a negative and a positive makes a negative. And I times I is I squared. I picked these particularly, these two sets of parentheses on purpose because something special happens in the middle here. This stuff in the middle cancels out. So 2i minus 2i is 0. And then I have a minus I squared. Remember, I squared is -1. So minus -1 turns into a +1. So this becomes 4 plus 1. And so this entire second part of this expression, 2 minus I times 2 plus I, becomes 4 plus 1. So this is a +5. And then at the end, when I'm on this step, I can combine like terms. I have a -6 and a +5. So that's going to be a -1 minus 15i. So that's the correct answer here to this warm-up question. So hopefully this rings a bell from the last video and just kind of getting your brain thinking some about imaginary numbers here. Okay. All right. So let's jump into our stuff for today. So for today, we are going to talk about conjugates of, sorry, I spelled conjugates wrong. Conjugates of complex, I'm going to put a slash, because really, remember, complex numbers are all numbers in the world, both real and imaginary. But right now, we're focusing specifically on the conjugates of imaginary numbers. Okay. So first of all, let's talk a little bit about conjugates. This is something that we've talked about numerous times this year. Conjugates are when we have two sets of parentheses where you have the same thing in both sets, but one is a plus and the other one is a minus. We actually just saw some conjugates in this warm-up question when we had 2 minus I times 2 plus I. Those are conjugates of each other. And so just to recap, when we saw it in that problem, let's go ahead and do this here. If I was to FOIL all of this out, a times a is a squared, a times -b is minus ab, b times a is plus ab, and positive b times negative b is negative b squared. What's special about conjugates is that every single time when I multiply two conjugates together, The terms in the middle cancel out, and I'm just left with the first thing squared minus the second thing squared. Okay, and this is consistent across the board. We've factored things this year. We call these differences of perfect squares. So like if I have x squared minus 9 and I want to factor this, well, this factors as x and 3 and 3, and one set of parentheses gets a plus and the other one gets a minus. So it's x plus 3 times x minus 3. Okay, so these are conjugates of real numbers. Now let's think about what a conjugate would look like if I had some imaginary numbers. So let's say that instead of this just being a plus b, this was a plus bi, and the second one was a minus bi. Okay, well, same kind of pattern is going to emerge here. If we FOIL this out, a times a is a squared, a times negative bi is minus abi, bi times a is plus abi, and then positive bi times negative bi. Well, positive and a negative makes a negative. B times b is b squared. But then don't forget on this one, there's I. So I times I is I squared. Okay. All right, let's think about this. Once again, negative abi and positive abi, those are like terms that cancel each other out. The only really different thing on this one is that there's an I squared. And remember, I squared is -1. So how does that affect things? Well, I still have an a squared at the front, but this time I've got a negative bi, I've got a negative b times a -1. And two negatives make a positive. So this ends up becoming a squared plus b squared. So look at the difference here. Okay, look at the difference here. The difference is when it's two conjugates of real numbers, it's a difference of perfect squares. But when it's two conjugates of imaginary numbers, it's a sum of perfect squares. Okay, so let's think about how this might work if I had a sum of perfect squares and I wanted to factor it. Let's say that I had something like x squared plus 9. Okay. Well, what does this tell me? If it's an x squared plus 9, in order to factor this, I still see perfect squares, but this time it's a sum. This time I'm going to have to use imaginary numbers. Okay. So let's think about how this would work. If I made two sets of parentheses, okay, so check this out. You see how this looks a lot like this. If I wanted to factor this, I want to fit it into this pattern right here. Okay. Well, a and a, that's whatever I square to get the first term. That would be x. So that's consistent. Okay. I get a plus and a minus. And then for this next one, I got to think about the number 9. Okay. Well, plus 9. Well, to get 9, I have to square 3. But the difference here is on this one, I have to use imaginary numbers to get this term right here to be a positive. Okay. And if you think about this, so here's the factored form of x squared minus 9, but you could always check this by just FOILing it out. Okay. Now I'm going to skip the part in the middle because I'm already fully aware that if I multiply two conjugates together, the middle terms should cancel out. So I'm going to skip that part. But if I try the rest of it, x times x, I get x squared. The middle terms are going to cancel out, but then when I try the terms at the end, positive 3i times negative 3i, well, 3 times negative 3 is -9. I times I is I squared. Remember, I squared is -1. So -9 times -1 ends up with a plus 9 when I'm done, and I finished. So I factored this sum of perfect squares. Okay. So if we were trying to kind of label these here, this is a difference of perfect squares, which I can factor just using real number conjugates. Okay. And then this right here is a sum of perfect squares, which I can factor, but I have to use imaginary number conjugates in order to do that. Okay, so quick example, just to put all those pieces together. Let's say that we had, if I told you to factor, and we had 36x squared plus 25y squared. Okay. When I look at this, 36 and 25, those are perfect squares, and x squared and y squared are perfect squares. So we could call this as a sum of perfect squares. Meaning, in order to factor this, we're going to have to use imaginary numbers. So if you want to, you can put two sets of parentheses with a plus and a minus. Okay, but now we got to get to work on thinking about what goes where. So first number, well, to get 36x squared, I have to square 6x. Okay, to get 25y squared, I have to square 5y. But since this is a sum of perfect squares, I need to make these last term in both sets of parentheses, imaginary, so that when I multiply together, I get the I squared, which turns this into a plus sign when I'm finished. So here's the factored form of that expression right there. Okay, so you can factor a sum of perfect squares if you use imaginary numbers. All right, last thing for today. It's a shorter video because I have some worksheet practice for you to try after. And I will put the answers to that worksheet in the OneNote folder. But we're going to talk about something called rationalizing imaginary denominators. Okay. In the world of higher level math, we do not really like to leave denominators with imaginary numbers in them, and I'll show you why when we get to a bigger example here at the very end. So what I mean by that is if we have something like, let's say that we have 3 minus 4i divided by 5 plus 2i. Okay. In the world of math, we don't like to have this imaginary component down here on the bottom. So as a result, we need to do some math with this in order to get rid of the imaginary part on the bottom. And we can do this using some perfectly valid or legal math moves. But we have to make sure that our math is consistent throughout and that we don't make any mistakes. So here's what we're going to do. When we want to rationalize imaginary denominators, what we do is we multiply the top and the bottom by the conjugate of the bottom of the denominator. Okay. So what I mean by that is the bottom of the denominator is 5 plus 2i. The conjugate of this is 5 minus 2i. So I'm going to multiply by that conjugate on the bottom. But remember, we've talked about with fractions, whatever you do to the bottom of a fraction, you must do the same thing to the top of the fraction. Okay? So we're going to multiply by this. This is just a fancy form of 1, because anything but divided by itself is 1. So it's valid for me to multiply by this. But from here, this is just a matter of me using proper multiplication in order to finish this out. So this is like a set of parentheses on top and bottom times another set of parentheses on top and bottom. So we're going to do a bunch of foiling here, and then we're going to simplify to get ourselves to a final answer. So let's try it. 3 times 5 is 15. 3 times negative 2i is negative 6i. Negative 4i times 5 is minus 20i. And then negative 4i times negative 2i is a plus 8i squared. Okay, so there's the top of my fraction. We'll simplify when we're done. Now, the bottom of this are conjugates, so I am fully aware that when I multiply these out, the middle terms are going to cancel out. So 5 times 5 is 25. Just to prove this to you, 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. And then 2i times negative 2i is minus 4i squared. These two terms right here, as mentioned, are going to cancel each other out. Okay, let's simplify this sum. So I squared in both of these instances is, a negative 1. Okay, so this term is going to become a minus 8. This term is going to become a plus 4 because negative 4 times negative 1 makes a positive. And so when I'm done here, I can combine these like terms. 15 minus 8 up on the top is 7. Negative 6i minus 20i is negative 26i. And then notice on the bottom here, there is no more imaginary component at all. It's just turned into 25 plus 4, which is 29. So here is the completely rationalized form of that fraction. They are equivalent to each other. So this original thing that I started out with is equivalent to this right here. But we rationalized it and got rid of the imaginary component on the bottom. Okay, let me show you one more of those, and then we'll finish with a big example to close ourselves out here. So once again, let's just rationalize. Again, this is going to be pretty much the exact same as the last one, just to show you this process one more time. Let's say we had 7 plus 3i divided by 2 plus I. Okay? All right, you can pause and you can try this if you'd like, if you want to work ahead of me. Or you can just watch. Remember, you should be writing everything down though anyways, because you can use all of your notes, all of your written notes and homework on quizzes for this unit. Okay, so we're going to multiply by the conjugate of the bottom, which in this case is 2 minus I. And then from here, this is just a matter of us using proper algebra to distribute these out and simplify. So 7 times 2 is 14. Okay, minus 7i. 3i times 2 is plus 6i. And 3i times negative I is a minus 3i squared. On the bottom here, 2 times 2 is 4. I'm going to skip the middle part because we already talked about it. The middle term should cancel out, so we can move to the end here. I times negative I is a minus I squared. Okay. Anywhere that I see this I squared, that's a negative 1. So we can change these. Negative 3 times negative 1 is a plus 3. And negative times a negative 1 is a plus 1. And so when I'm finished here, I can write my final answer. 14 plus 3 is 17. Negative 7i plus 6i is a minus 1i, or you can just write minus I. And then 4 plus 1 is 5. So here's my final answer for that. Okay, so that's the process of rationalizing an imaginary denominator. Now, from our last example, we'll call this just our big problem of the day. I did put one of these on the worksheet practice as well. So for our big problem, let's add these two fractions together. Okay, so here's what I've got. 3 plus 2i divided by 3 minus I plus 9 over 20. Okay. All right, and this is a super weird problem because I've got an imaginary denominator on the first one. I've got a real number. So here's my imaginary denominator, and then a real number denominator on the second one. And I'm being asked to add these together. So this is one of the reasons why we don't like to have imaginary stuff at the bottom of the denominator, because what I'm going to do on this problem, before I even start worrying about that plus 9 over 20, is I'm going to rationalize this denominator right here. Okay. So what we were just doing in terms of multiplying by the conjugate, I'm going to do that on the top and bottom of this fraction. Just to get us started, I'm going to see, hey, can I change that imaginary component into a real number? Okay. So I'm not even going to worry about this plus 9 over 20 until I completely finish this. Then I can bring that back into play. So let's try this part first. So if I'm going to do this, 3 times 3 up on top is 9. 3 times I is a plus 3i. 2i times 3 is a plus 6i. And then 2i times I is plus 2i squared. Okay. All right, on the bottom, conjugates. So the middle terms are going to cancel out. 3 times 3 is 9. Negative I times positive I is a minus I squared. Okay, everywhere we see an I squared, that can be replaced with a negative 1. So 2 times negative 1 is minus 2. Negative times a negative 1 is a plus 1. Okay. And from here, we can get a simplified form of this first fraction. So 9 minus 2 is 7. 3i plus 6i is a plus 9i. And then on the bottom, 9 plus 1 is 10. All right, now let's bring this part back into play. So now what I'm doing is I'm adding 7 plus 9i divided by 10 plus 9 over 20. At this point, this is a much nicer problem for us to work through because now we at least have two denominators that look somewhat alike in the fact that both of them are real numbers. And I know what to do from here. So I know that the common denominator between 10 and 20 is 2, and I have to have a common denominator to add fractions. So what I can do here, the common denominator between 10 and 20 is 20. So what I can do here is I can multiply the top and bottom of this first fraction by 2. Remember, whatever I do to the bottom, I got to do the same thing to the top. And once I do that, now the denominators on both of these, 10 times 2 is 20, and I already have a 20. So now I can put all of this on the same fraction. Okay. The only thing I got to be careful of here is making sure that I distribute this 2 correctly. Okay, so let's try it. 7 times 2 is 14. 9i times 2 is 18i. And then I can bring this plus 9 right over here. So plus 9. Okay, got it all in the same fraction now because I had a common denominator. And last but not least, we can combine like terms up on the top here. 14 plus 9 is 23 plus 18i, all divided by 20. Okay, so here's my final answer when I add these two fractions together. So again, before I try to add these, Got to have a common denominator, but finding a common denominator at the beginning would have been really difficult on this problem because I had a 3i and a 20. However, by rationalizing this first denominator and getting it to be a real number, then I was able to do the fraction work a little bit more simply and quickly, and I could get to my final answer. All right, that concludes this video. So remember, I'm going to put some practice. There's a practice worksheet linked in the Google Doc, and I will put the solutions to that worksheet here in the OneNote folder as well. So check that out. It's not going to be for a grade. The teacher is not going to collect it. The substitute is not going to collect it. However, any work that you do on that worksheet, you may use that work when you take your quiz. There's no copies of the worksheet, so you're just gonna have to work on it on notebook paper. But give it a shot, check out the solutions, and hopefully it's making sense. Bye, y'all.